Hi everyone, and welcome to this tutorial on CMD and vectorization. My name is Dimitra, and today we'll explore how to take advantage of HPX capabilities to write fast, efficient code using parallel execution and CMD instructions. We'll start by understanding how CMD works in modern C++ through the studCMD API, and then see how HPX makes it easy to apply CMD through parallel execution policies. Finally, we'll put everything together with a real-world example, applying a blur filter to an image. For this tutorial, you need to have your HPX installation complete and know how to compile and run an HPX application. For this, we have a different tutorial with a Hello World example, which I will link here. Please ensure that your HPX build has support for CMD using the data parallelism module. So, to enable CMD support, make sure you build HPX with the following CMake flags: HPX with datapar on and HPX with datapar backend stud experimental CMD. But before we jump into the code and HPX specifics, let's take a moment to understand what CMD actually is and why it matters. CMD stands for Single Instruction Multiple Data. It's a way for modern CPUs to process multiple data elements with a single instruction simultaneously. Imagine doing the same math operation, like addition or multiplication, on several numbers at once, instead of one by one. This can make certain programs, especially those working on large arrays or images, much faster. With that in mind, let's explore now how CMD works and how modern C++ and HPX help us write CMD-enabled code efficiently. Let's talk about CMD on x86. One of the main challenges with CMD is that there is no standard C function to explicitly say, vectorize this. While some intrinsics do exist, they're often low-level and hardware-specific. Traditionally, to fully control CMD, you'd need to write assembly, something complex and error-prone. The alternative to that is to rely on the compiler's auto-vectorization. Compilers like GCC or Clang can sometimes detect loops that operate on simple data types like doubles and automatically convert them into vectorized versions. So for example, if a loop processes 8 doubles, the compiler may use a 512-bit register to handle all 8 in parallel, performing thus 8 additions in the time it would normally take to do just one. The essence of vector operations is that you have large registers that don't just contain one double, 64 bits, but up to 512 bits, which gives us 8 doubles. When you load 8 doubles in and do an addition operation, these 8 additions happen at the same time with the same speed as if you were adding just one double. This gives you an effective speedup of up to a factor of 8. But how do we program this? Very few people want to write assembly code, right? So how do we do CMD in C++? C++26 introduces studCMD. For C++ versions earlier than 26, CMD still exists, but it's in the experimental namespace. So in studCMD T is any type that can be vectorized, usually integral types such as integers, longs, doubles, or floats. The number of values you can put into a CMD T depends on the architecture. Some architectures support vectorization for doubles, some have larger vector registers. In the end, an object of type CMD T behaves analogous to a scalar T. CMD stores and manipulates many values. You can think of it as a struct that contains 4 or 8 T values, depending on what the architecture supports. All operators are overloaded so that your code generates efficient vector instructions without needing any assembly code. So let's have a look at some examples. A CMD can be initialized with a single value, which will be copied across all its lanes. So, if it contains 4 integers and you initialize it with 5, all 4 elements will be 5. You can also initialize it with a lambda. The lambda gets the index of the lane, so you can return a different value for each element. That's a nice way to do more complex initializations, such as filling it with -2, -1, 0, 1. There is also a reduce function which performs a horizontal operation. So for instance, summing across all lanes of the CMD register to get a single value. You can also apply math operations to CMD types. Instead of producing a scalar result, the operation is applied to each element and produces a new CMD. The print function I use just accesses each element inside the CMD one by one and prints them out. That's another example of how to access and work with CMD. Let's see now how we can use CMD with algorithms. In a typical non-CMD loop, you just iterate over an array and apply a function to each element. So we have a vector of floats called data, and we iterate over this vector and we just do something to its data. This is pretty straightforward. We have one element at a time, one operation per iteration. Now, instead of writing the loop manually, you can express the same logic more elegantly using an algorithm. So you have stood for each, data begin, data end, and then our function does something. This works with both sequential and parallel versions depending on which execution policy you choose. So we can also have stood for each, stood execution par, data begin, data end, and then our function does something. This gives you parallelism but not vectorization yet. Now let's apply the same concept with CMD. So here's the idea. You iterate over the data item from 0 to n and you load n elements into a CMD register. Instead of operating on one float, we operate on a CMD float which contains 4 or 8 floats. And then you call a function do something that actually receives a CMD value. So we process multiple values simultaneously using CMD instructions. But there is one complication. What if the total number of elements n cannot be divided by the CMD size? For example, if you process 8 elements at a time and have 18 elements total, the last 2 elements won't fit into a full CMD register. So to fix this, we use 2 loops, one for the vectorized part and one for the scalar tail. So yes, vectorizing loops is more complicated. You have to split the vectorized part from the tail and maintain 2 paths of logic. But wouldn't it be nice if we didn't have to write this boilerplate ourselves? And here is where HPX comes in, where you can just write HPX for each, HPX execution CMD, data begin, data end, and then call our function do something. And then HPX will automatically vectorize the loop and handle the leftover tail elements for you. You can even combine this with parallelism by just changing the execution policy to par CMD. So we have HPX for each, HPX execution par CMD, data begin, data end, and then call function do something. This gives you the best of both worlds, parallel threads and CMD execution with no manual loop splitting. So far, we've seen how HPX can be used to perform vectorized computations on one-dimension data like vectors. But CMD becomes even more powerful when applied to real-world use cases, like image processing. In this next example, we'll load an image and apply a simple blur filter using HPX with CMD execution policies. It's a great way to show how data parallelism can help with compute-heavy tasks. We are using a lightweight BMP library called EasyBMP, which lets us access and manipulate each pixel directly. I've downloaded the EasyBMP source code into my include directory, and I'm using it directly from there. No separate installation is needed. So, let's begin with our main function. We start by loading the image. Alright, so first, I'm going to create an instance of the BMP class. This will represent the image we're going to load. So I'll just write BMP input. Next, I want to read an image file called image.bmp. To do that, I'll use the read from file method, but I also want to check whether that operation was successful. So I'll wrap it in an if statement. So let me write that. If not input read from file image BMP. So the method returns true if the image loads successfully and false if it fails. So for example, if the file doesn't exist or there is a problem reading it. In that case, I want to print an error message and return. We get dimensions of the image, width and height. So we do int width equal input tell width, and then int height equal input tell height. We create the new output image with the same dimensions as the input one. So we set the size to width, height, and we also set the bit depth to 24 for the RGB format. Before applying the blur, we copy the input image into the output. This preserves the border pixels, which we don't modify. We iterate over the image dimensions and we do pointer output x, y equal pointer input x, y. So both input and output return pointers to the pixel at position x, y. So these are not the pixel values themselves yet. That's why we use the asterisk to dereference the pointer and access the actual pixel structure. Then we call our blur function. So blur image input, output. And finally, we save the blurred result as a new BMP file. So we do output, write to file, and let's name it blurred BMP. Now let's have a look at the function that performs the blur. It takes a read-only reference to the input image and writes the result to the output image. First, we get the dimensions of the image, width and height, the same way we did before in our main function. Then HPX needs a range of values to parallelize over, so we will use a vector of integers called rows, which gives us that range. So all row indices from 1 to height -2. So we have to exclude the first and the last rows because we need to access a pixel's top and bottom neighbors, and those don't exist for border pixels. We want to fill the vector rows and values starting from 1 up to height -2. So we iterate over the rows, and each element, rows I, will have the value I plus 1. Now we'll perform the blur using HPX for each. So we use the parCMD policy, which enables both parallel and vectorized execution. We need to define the range of pixels we want to process, so we start from rows begin up to rows end. Inside our lambda, each thread processes one row of the image. So we look through each column at that row, and we're visiting every pixel, except the first and the last rows, as we just said before. So for each pixel at x, y, we grab its vertical neighbors, one from above, one from the current row, which is this pixel that we're talking about, and one from below. So we have const RGBA pixel pointer top equal input x, y -1 for the row above. Then we have the mid pixel, which is just input x, y. And then we have the bottom pixel, which is input x, y plus 1 for the row below. Now we will use a helper lambda to do a simple vertical blur by taking a weighted average of 3 values. So for each pixel, the new value is 25% of the top pixel, 50% of its current value, so the mid pixel, and 25% of its bottom value, giving us this formula. So we have 0.25 of A plus 0.5 of B plus 0.25 of C. Then we clamp the value to ensure that the result lies between 0 and 255, which are the acceptable values for the image pixels. So now we will use this function to apply the blur separately to the red, green, and blue channels. We have output x, y for the red channel equal blur channel, the function we just created, and then we give the 3 channel pixels, so top red, mid red, and bottom red. We do the same for the other 2 channels, so the green and the blue one. And this way, each color channel is blurred independently, and then the result is written back to the corresponding pixel in the output. Thanks to HPX parCMD policy, we get parallelism across pixels and CMD inside each thread. This makes it fast, scalable, elegant. To make the EasyBMP code work, the only thing you need to do is add the EasyBMP CPP file to your CMake project. So, in your CMake lists.txt, instead of just compiling HPX CPP, you should write add executable HPX, CPP, which I guess you already had, and then include EasyBMP CPP. This tells CMake to compile both your main HPX source file and the EasyBMP implementation file together, so everything is linked properly. So now it's time to run our code. I'm using this image of a tiger running in the snow. As you can see, the result is nicely blurred in the vertical direction. Sharp edges are softened and the transitions between light and dark areas look much smoother. This kind of blur is simple, but it highlights how well HPX scales with structured, pixel-wise operations. You can make the blur stronger by applying the filter multiple times. So, simply use a for loop to call your blur image function as many times as you want. And that wraps up our tutorial on CMD and vectorization with HPX. We looked at how to use studCMD in C++, explored HPX CMD and parCMD execution policies, and applied everything in a real-world blur filter example. I hope this gave you a clear, practical intro to writing fast and efficient code with HPX and CMD. Thanks for watching and see you in the next one.